Hi everyone, I am Santi from Department of Mathematics and Statistics, Bhavans Vivekananda College. I am here with my lesson 27 of linear algebra in vector spaces. In this lesson, I am going to explain few more examples on matrix of linear transformation. Now let us look at the concept coordinate vector of T of x. So let V, W be two vector spaces and let B, C be bases for V and W respectively, and then let T from V to W be a linear transformation. So let us draw the diagram for this. I have a vector space V. We have another vector space W. So I have this is V and this is W, and we have T. This V has a basis B and W has a basis C, and T is a linear transformation from V to W. This is what given to us. Then suppose this B is having the elements. Let me take. Let B is equal to set containing B1, B2 and so on Bn. Then whenever there is a vector x, and we all know x belong in V, x belong to V implies we have x is equal to R1 B1 plus R2 B2 plus and so on plus Rn Bn, because every vector in the vector space can be written as a linear combination of basis vectors. Then implies I can say the coordinate vector of x corresponding to the basis B is nothing but it is obtained by taking the coordinates from this Rn. So by taking these coordinates R1, R2 and so on Rn, which are scalars. Now whenever x is there, let us come here. T of x will be there in W. T of x will be in W. And suppose then T of x is there in W implies, so let me write this. X belong to V implies T of x belong to W. Then what do we mean by T of x? T of R1 B1 plus R2 B2 plus and so on plus Rn Bn, because x is written as this one, this statement. Now T is a linear transformation. I can write this as R1 into T of B1 plus R2 into T of B2 plus and so on plus Rn into T of Bn. Then what will be the, now let us see what is the coordinate vector of T of x corresponding to the basis C. This is what we want here. Then this will be nothing but R1 into, let me take this, R1 into the coordinate vector of T of B1 corresponding to basis, this will be C plus, why? Because T of B1 will be there in W, right? R2 into the coordinate vector of T of B2 into C plus and so on Rn into the coordinate vector of T of Bn into C. This is nothing but I can write this as a product of two matrices. First one is it will have column T of coordinate vector of T of B1 with respect to C. This is the first column. Coordinate vector of T of B2 with respect to C, and so on. Coordinate vector of T of B1, Bn with respect to C. This is into, you can observe this, if you multiply this with this column vector R1, R2 and so on, Rn, you can observe this product is nothing but product of these two matrices. Coordinate vector of T of B1 with respect to C into R1 plus, you can observe this will be the coordinate vector of T of x with respect to C. Now this is nothing but I can say this matrix is the coordinate matrix of linear transformation of T with respect to the basis B and C into, and this is nothing but coordinate vector of x with respect to the basis B. Therefore, we have this formula. The coordinate vector of T of x with respect to the basis C is nothing but the matrix of linear transformation of T with respect to the basis B and C into the coordinate vector of C with respect to the basis B. Now let us look at problems basing on this. Example 1. So here it is given B is equal to set containing B1, B2, B3, B a basis for vector V, then find T of 4B1 minus 3B2 first, where T is a linear transformation from V into V itself, whose matrix relative to B is given by coordinate matrix of T relative to basis B is 0, 0, 1, 2, 1 minus 2, 1, 3, 1. Let us look at the solution. So here you are given B is a basis for V and T is a transformation from V into V. That means I have this one. V to V itself T is a transformation and the basis for V is B1, B2, B3. This is B. Even here also you will have the same B1, B2, B3. This is what given to us. Now let us write all this. So B is equal to B1, B2, B3, and then this is a domain I can say, and T from V to V is a linear transformation. This is basis for both domain and codomain, because domain and codomain are the same. Now what is given here in the question, x is you are asked to find T of 4b1 minus 3b2, right? So first let us take that is if you compare this with T of x, then x is equal to 4b1 minus 3b2. Now where is this x? X is there in the domain. Then how can you write x as, because we have this one, no? We have coordinate vector of T of x with respect to the basis B is equal to matrix of linear transformation t, both bases are the same, into coordinate vector of x with respect to b. Now we have this with us, and we know what is, we should know coordinate vector of x with respect to b. So first we'll find this, I'll give this, we have to find. First to find coordinate vector of x with respect to b. How do you get this? So x is equal to 4b1 minus 3b2. We will write it as, I can say this is 4 into b1 plus minus 3 into b2 plus 0 into b3. That is a linear combination of b1, b2, b3. Because you have to find the coordinate vector of x with respect to basis b. So b has the elements b1, b2, b3. So write it as a linear combination of b1, b2, b3. That implies if you write that, you will get the coordinate vector of x with respect to b is nothing but 4 minus 3, 0. And now what do we have? The coordinate vector of x with respect to b is nothing but the matrix of linear transformation into coordinate vector of x with respect to b. So what is the matrix of linear transformation given to us? It is given here as 0, 0, 1, 2, 1 minus 2. So 0, 0, 1, 2, 1 minus 2, and the last one is 1, 3, 1. And then into what is coordinate vector of x? You got it 4 minus 3, 0. So multiply this. You will get 0 plus 0 plus 0, and then 8 minus 3 plus 0, and then 4 minus 9 plus 0, which is equal to 0, 5 minus 5. So this is a coordinate vector, but we have to find, they didn't ask coordinate vector actually, they asked you to find here t of x only, t of 4b1 minus 3b2. Which implies I have the coordinates of t of 4b1 minus 3b2 is equal to 0, 5 minus 5 with respect to b, implies t of 4b1 minus 3b2 is equal to 0 into b1 plus 5 into b2 minus 5b3. So the formula for this will be 5b2 minus 5b3. Now let us look at the second example. The mapping T from P2 to P2 defined by T of A0 plus A1T plus A2T square is equal to A1 plus 2A2T is a linear transformation. Then first bit, find the B matrix, that is matrix of linear transformation. B matrix, matrix of linear transformation for T with respect to basis B, where B is equal to set containing 1T square, that is the first one. And the second bit is verify that this one, coordinate vector of T of P with respect to basis B is equal to matrix of linear transformation of T with respect to B into coordinate vector of P with respect to the basis B. So let us look at the solution. So here you are given T from P2 to P2. This is P2 and P2. Both have the same basis, I will see, with 1T square, and here also 1T square. This is B, and this also has the same basis, B. Right. Then, so here you are given This is a linear transformation. And then B is 1t t square. Now you have to find the B matrix. How do you find the B matrix? For each element with respect to basis B. So what do you have to find? You have to find first t of 1, t of t and t of t square. So t of 1 is equal to, and you are given here linear transformation definition, t of a0 plus a1t plus a2t square is equal to a1 plus 2a2. So what is that you have? Let me write that. We have t of a0 plus a1t plus a2t square is equal to a1 plus a2t. So what will be t of 1 means I should write t of 1 as 0 plus not 0, I have a constant 1 I have here. So it is 1 into 1 plus 0 into t plus 0 into t square. So this is a0, a1, a2. So a1 plus a2t, this is a0, this is a1, a2. So a1 is 0 plus a2 is 0 into t, which is equal to 0. Then t of t is equal to t of 0 into 1 plus 1 into t plus 0 into t square. So this is a0, a1, a2. So you have here a1 plus a2t, 1 plus 0 into t. This is equal to 1. T of t is 1. And then t of t square. So t of t square is equal to t of 0 into 1 plus 0 into t plus 1 into t square. So here a0 is 0, a1, a2. So it will be a1 plus 2at. a1 is 0 plus 2 into a2 into a1 plus, a2t. The formula is a1 plus a2t to, or what it is, a1 plus 2a2t. So this is 2a2t. So this will be 2 into 0. Anyway, this is 0 only. And here also it is 2 into 0. Because the formula, let us check once. Yeah. a1 plus 2a2t. This is what given to us. So this will be 2 into 1 into t square. a2t, not t square, it is t. So this will be equal to 2t. So what do we have now? T of 1 is equal to 0. T of t is equal to 1 and t of t square is equal to 2t. Now again we have to find coordinates with respect to b, coordinate of t with respect to b, and coordinate of t of t square with respect to b. How do we get that? You have to t of 1 is equal to 0, and then you have to write it as linear combination of 1t t square, which is the basis for the codomain. Here 1t t square. This one. So this I will write it as 0 into 1 plus 0 into t plus 0 into t square. That implies coordinates vector of t of 1 with respect to b will be equal to 0, 0, 0, first one, and then next one t of t is equal to, what did you get? 1. So 1, how do I write? 0 into, not 0, it is 1 into 1 plus 0 into t plus 0 into t square. So then what is the coordinate vector of t with respect to 1t t square? This is 1t t square b. So will be 1, 0, 0, and similarly t of t square is 2t, which I will write it as 0 into 1 plus 2 into t plus 0 into t square. So coordinate vector of t square corresponding to the basis b will be equal to 0 to 0. Therefore, my matrix of linear transformation T, that is with respect to the basis, only one basis, because both have this, even we'll write it as, we call it as B matrix, because both domain and codomain have the same basis. It will be equal to, what is the first column is 0, 0, 0, the coordinate of T of 1, T of 1, and the second column is, this is coordinate of T of 1, and second one is, this is 1, 0, 0, which is the coordinate of T of T with respect to the basis B, and the third one is 0, 2, 0, this is with respect to the T of T square coordinate with respect to basis B. So this matrix is 0, 0, 0, 1, 0, 0, 0, 2, 0, matrix of B matrix. We call it as B matrix. Our A bit is over. What is our B bit? Verify B bit is asked. Verify coordinate of T of P with respect to basis B is equal to coordinate matrix of linear transformation of T into coordinate of T with respect to B. This is what you have to verify now. Now let us see, we know only this matrix now. We have to find these two. So first, what is coordinate of P with respect to basis B? What do you mean by that? P is any polynomial that is coordinates of a0 plus a1t plus a2t square with respect to basis B is nothing but column matrix 0 for a0, a1, a2. Now, what is T of P? T of P is given as a1 plus 2 a2t, that I will write it as constant 1 into a1, not 1 into a1, we should write it as a1 into 1. a1 into 1 plus 2a2 into t plus 0 into t square. This you have to write it as a linear combination of 1t square. So this will be then, which implies the coordinate vector of T of P with respect to the basis B a1 to a2 0. So now what do we have to verify? What is coordinate this one? Matrix of linear transformation, this is nothing but LHS into coordinate of P with respect to B. What did you get? Matrix of linear transformation. This is 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0 into, next you have to multiply with RHS, coordinate of P with respect to basis B. What is that? Coordinate of P with respect to basis B. This is what you have to get. Coordinate vector of P with respect to basis B. So that is A1, one second, what is that? A0, A1, A2. So this is equal to A0, A1, A2. Which is multiply this, we will get 0, 0 plus A1 plus 0, and then 0 plus 0 plus 2A2, 0 plus 0 plus 0, that is equal to A1 2A2 0. This is RHS. So you can observe this one is 0 A1 A2 A2 0, and even this is also the same A1 to A2 0. Therefore, coordinate vector of T of T with respect to basis B, that is matrix of T relative to B into coordinate vector of P when it is equal to A1 to A2 0. Therefore, it is verified.